Okay, Jason, what I want to do is I want to explain a little bit more about problem number 33 and show how you can figure it out using math and our equilibrium expression. You don't have to do that for the problem, but I just want to show you that it works and that there is a way to figure out. I would just use like the way that I taught you, showed you how to do it. Just try to figure it out intuitively. Okay, so in problem 33, it said that you're going to add a 1 atmosphere of Cl2 to your equilibrium amount, and then you're supposed to pick which one of the four graphs happens to the chlorine. Okay, and the one that I said you pick is that, right, so here you're at equilibrium, then you're going to add your chlorine, and what happens is you get a spike in it, I said. Okay, and then what happens is that the chlorine is going to go down, all right? But it's not going to, whoops, it's not going to go all the way down to the point it started. It's still going to be higher than that. Sorry, this goofy graph should have been, okay, more like this. Okay, all right. And what I wanted to show you is that it doesn't go below the beginning. Okay, all right, and it doesn't come to where it is, but it actually goes a little bit high. So let's go over that, how you can do that mathematically. So we found that the Kp is 0.27, and so what we did is we added 1 atmosphere of chlorine to the equilibrium amounts, and so what that did is that increased the chlorine to 1.4, while these guys stayed the same. Okay, so that's what happens right here. You get an increase of your Cl2. All right, all right. Now what we want to determine. Okay, so you have your equation. So the equation goes from PCl5 to PCl3 plus Cl2. Okay. Um, okay. So what we want to know, and just formalities, we want to know what's going to happen to this reaction. Isn't it going to go to the right or to the left when you add the chlorine? Now, from Le Chatelier's principle, you know if you add substance to one side of the equation, it will drive the equation to the left. All right. Uh, so we know from Le Chatelier's principle that's what happens. But there is another way to figure this out, and that's using the reaction quotient. Okay, and the reaction quotient, I show down here, but let's want to explain it, is that if the Kp is greater than the Q, so you find the Q, and that means the reaction will go to the right. If it's the other way around, where the Q is greater than the K, the reaction will go to the left. And the way I remember this is K is greater than Q goes to right, right? There are different ways you can think about that. If they were equal, then you're at equilibrium. So the reaction quotient is essentially the same as the equilibrium expression. So Q is equal to Cl2 times the PCl3 divided by the PCl5. And you put in the numbers and do the math, and you can see that's 0.93. So 0.93 is indeed greater than 0.27. So that means Q is greater than K. So the reaction will go to the left. Okay. So we'll go to the left, just like we expected from Le Chatelier's principle. All right. So let's figure out the final amounts of each one of these after it reaches equilibrium. So what's going to happen is you added the Cl, okay, and then what's going to happen is the Cl is going to decrease to try to get back to equilibrium. So let's see what the final Cl2 is, see if it is above our starting point. Okay, so here's our ice table. So you have 0.6, 1.4 goes to 1.4 and 0.4. So this is our added Cl2. there's going to be, so the reaction is going to go to the left. That means we're going to lose some x, and we're also going to lose some x over here, but we're also going to get x over here. So when you put those all together, you can fit, this is the amounts of each species. Okay, so now what we have is Kp is equal to 0.27 equals to 1.4x, so product over reactant times 0.4x. Okay, I added an extra, forget that. Divided by the reactant, 0.6 plus x. Okay. Now this is a little bit complicated, but I'm sure you've gone over it. And so what you need to do is expand for the equation and get x, and so forth. And so here I'm just expanding it. So so I just multiply both sides by 0.6 plus x. And that's how I got this. Okay, then I just multiply these two to get this. And then added, I did the quadratic equation. I just multiplied these two together, and then I added these to the other side, and so I get this equation here, 0.56 minus 1.8x plus x squared. And then there's, you can just find a quadratic equation solver, and when you do that, you get two values, and here's two values to get. All right, not both will work. So if you take the 1.86 and put it in these values here, you'll see you get a negative number. But if you put the 0.214 in these values, you see that you get positive number. So we're just going to use the 0.214 as x. So let's see what our final concentrations are. Okay, so now we have 0.6 plus 0.21. I left off 4 equals 0.18, so that's the final concentration of the PCl5. The Cl2 is 1.4 minus 0.21, 1.9, and the PCl3 is 0.19. All right, so so notice is that our original pressure of Cl2 was 0.4, so you can see that it did increase, okay, but it dropped down from the 1.4 that we started with, okay, so that's what we said in the graph. So you add, goes up to 1.4, and then what it does, it tails off until 1.19, okay. So just to double check if these values actually work, I plugged them all in, and you see that we got 0.27, so that's good. All right. All right. So I just want to show you how that works. You don't need to do that for the problem, but if you think it out, okay, but you can figure it out. All right. Now the other thing I wanted to do, it's that I'm not sure how clear it gets through, but is looking at Ka and pKa. So pKa is Ka is a measure of acid, just called acid dissociation, and basically it is that Ka, a real simple version is Ka is equal to the amount of base, conjugate base, over the amount of acid. I know you have over here is actually another term, but so basically this is it. So if you have high acid, okay, you will have a low Ka. All right. So so it turns out that pKa. So when you see pKa, don't get worried about it because it's a lot in the same way of thinking about pH. So you know that if you have a low pH, the solution is acidic. Well, you kind of can infer the same thing for pKa. If you have a low pKa, it's also going to be acidic. Right, so how is pKa found? Right, I'm sure you've gone over this, but it's simply the minus log of Ka, and Ka is 10 to the minus pKa. So let's look at two examples. Let's say Ka1 is 10 to the minus 4th, and Ka is 10 to the minus 8th. Okay, So what this means, so which one of these two is a bigger number? We can see that, hopefully you can see that this number here is bigger than this number. All right. Okay. So, all right. So it's a bigger number. All right. So, or okay. So the bigger number is going to mean it's more acidic. All right. Okay. So 10 to the fourth is bigger than 10 to the minus eighth. Now, what is the pKa of both? All right. Well, pKa1 is equal to minus log 10 to the minus fourth equals 4, and pKa2 is 8. So you can see, like in pH, if you have a low pKa, you actually have a high Ka, which means it's more acidic. Okay. All right. I'll add this one with the other video as well. Okay.